July 1st, 2025 started like any other night at the Atlas Telescope facility in Chile. The robotic observatory was scanning the southern sky for asteroids that might threaten Earth, clicking images every 30 seconds and comparing them to previous observations. But at exactly 14 hours and 37 minutes universal time, something appeared that shouldn't exist. A faint dot of light was moving against the background stars, but it was moving wrong. Too fast, in the wrong direction, from a place where nothing should be coming. The automated detection system flagged it immediately. Within hours, observatories worldwide were confirming what the Chilean telescope had found. The preliminary calculations were disturbing. This object wasn't bound to our solar system. It would pass through once and never return. We had discovered our third confirmed visitor from interstellar space. The first two had been strange enough. Oumuamua in 2017 had behaved like no asteroid anyone had seen before. 2I/Borisov in 2019 looked more normal, but carried chemistry from an alien star system. Now this new visitor, designated 3I/ATLAS, was arriving with its own mysteries. What made this discovery different was the timing. Unlike its predecessors, which were discovered when already leaving, 3I/ATLAS was caught early. We would have months to study it as it approached the Sun. The object was still 4.5 astronomical units away, roughly the distance to Jupiter. But even at that distance, something was happening that made astronomers worldwide take notice. This wasn't just a cold, dead rock. It was active. A fuzzy envelope of gas and dust surrounded the invisible nucleus, creating what astronomers call a coma. This interstellar wanderer was already breathing in the vacuum of space, releasing material frozen for millions of years during its journey between stars. The speed measurements were staggering. 130,000 miles per hour, fast enough to cross the entire United States in less than 3 minutes. But this wasn't just impressive velocity. It was the signature of something that had traveled unimaginable distances to reach us. As word spread through the astronomical community, there was an undercurrent of unease. The object's brightness, its activity level, its perfect trajectory for observation from Earth, all seemed almost too convenient. Within 24 hours, every major telescope on the planet was being redirected toward this cosmic visitor. The Hubble Space Telescope interrupted its scheduled observations. The James Webb Space Telescope added it to priority targets. Ground-based observatories coordinated their efforts. But as the first detailed observations began streaming back, astronomers realized they weren't just studying another space rock. They were looking at something that challenged everything they thought they knew about what should be possible for objects wandering between stars. The universe had delivered a mystery to our doorstep, wrapped in starlight and traveling faster than anything had a right to travel. The question that would haunt the next several months was simple. What exactly had we found? To understand why 3I/ATLAS shocked astronomers, you need to understand what speed means in space. When we launch rockets to escape Earth's gravity, they need to reach 25,000 miles per hour. But 3I/ATLAS was moving at 130,000 miles per hour. That velocity tells a story about where this object came from. Objects born in our solar system are gravitationally bound together by the sun's influence. Even the fastest comets eventually return home, following elliptical paths that bring them back within millions of years. But 3I/ATLAS was following what mathematicians call a hyperbolic trajectory. Instead of a closed loop, its path through space opens into infinity. It's like the difference between a ball thrown gently upward, which falls back down, and a bullet fired so fast it escapes Earth's gravity forever. The technical measurement that proves this is called orbital eccentricity. Normal solar system objects have eccentricities less than 1. 3I/ATLAS had an eccentricity of approximately 1.7. Not only was it unbound from our solar system, it was moving so fast that even Jupiter's massive gravitational influence could barely nudge its trajectory. This speed carries crucial information. When astronomers calculated the object's velocity relative to nearby stars, they found it was moving at roughly 25 kilometers per second. That's the kinetic signature of something that formed in a completely different stellar environment. Think of it like accent recognition. Just as a person's accent tells you where they grew up, an object's velocity tells you about the gravitational environment where it was born. 3I/ATLAS spoke with an accent that marked it as definitively foreign. At its current velocity, 3I/ATLAS would need roughly 300,000 years to travel from the nearest star. More distant stars would require millions of years of travel time. This wasn't recently ejected debris from a nearby stellar system. This was an ancient wanderer that had been traveling through the galaxy since before human civilization existed. During its journey, entire ecosystems on Earth had evolved and gone extinct. Yet through all that time, this small piece of another world had been racing through the cosmic void. The discovery statistics made the find even more remarkable. Survey systems like Atlas scan millions of square degrees of sky and catalogue hundreds of thousands of objects. In nearly a decade of operation, they had found exactly one confirmed interstellar visitor moving at these extreme velocities. The rarity wasn't because interstellar space is empty. Theoretical models suggest thousands of such objects should exist within every cubic light-year of our galactic neighborhood. The problem is detection. These cosmic bullets move so fast and reflect so little light that they're nearly impossible to spot until they're already racing through our inner solar system. As 3I/ATLAS continued its approach toward the Sun, astronomers realized they were witnessing something extraordinarily rare. A messenger from another star system, moving at velocities that spoke of unimaginable distances and cosmic timescales that dwarfed all human experience. But speed was just the beginning of what made this visitor strange. Space is supposed to be empty, cold, and dead. Objects wandering between stars should be frozen solid, their surfaces sculpted only by cosmic radiation over millions of years. So, when astronomers looked at 3I/ATLAS and saw something that looked alive, breathing gas into the vacuum, it changed everything they thought they knew about interstellar visitors. The fuzzy envelope surrounding the object is called a coma, from the Latin word for hair. It's what happens when a comet gets close enough to a star that the sun's heat begins to warm its frozen surface. Ice transforms directly from solid to gas, creating an atmosphere around what had previously been a dead rock. But here's what made 3I/ATLAS so puzzling. Most comets don't start showing significant activity until they're closer to the Sun than Mars. This visitor was already producing a detectable coma when it was farther out than Jupiter, at distances where the Sun's heating should have been too weak to drive much sublimation. The coma itself was beautiful in a ghostly way. Hubble's images showed a teardrop-shaped cloud of dust and gas, glowing softly as it reflected sunlight. The material flowed away from the nucleus like breath on a cold morning, creating patterns that revealed invisible forces shaping this cosmic dance. What really caught astronomers' attention was the scale of this activity. The visible coma stretched thousands of miles from the central nucleus, and spectroscopic observations suggested the gas cloud extended even farther. For such a small object, estimated to be only a few kilometers across, to generate such an extensive atmosphere seemed almost impossible. The composition of this interstellar breath was equally mystifying. When the James Webb Space Telescope analyzed the spectral signature of the gases being released, it found something unprecedented. Instead of the water vapor that dominates most comets, 3I/ATLAS was exhaling primarily carbon dioxide. The ratio was stunning: 8 parts carbon dioxide to 1 part water. Most comets in our solar system show the opposite pattern, with water dominating by factors of 10 to 100. Even the most water-poor comets rarely exceed carbon dioxide ratios of 2 to 1. This wasn't just unusual chemistry, it was chemistry from an alien world. The molecular signatures suggested formation conditions, unlike anything in our solar system, perhaps around a different type of star where carbon-bearing compounds dominated over water during planet formation. But the mystery deepened when astronomers tried to understand how such a small nucleus could maintain such extensive gas production. The energy budget didn't add up. Solar heating at 3I/A TLAS's distance should have been insufficient to drive the observed activity levels. The activity patterns also seemed strangely controlled. Unlike typical comets, which show chaotic brightness variations as they tumble, 3I/A TLAS maintained remarkably stable brightness. Its outgassing appeared almost managed. Some researchers began to wonder whether they were looking at a natural object behaving in unexpected ways, or something else entirely. The controlled activity, the unusual chemistry, the perfect timing of its arrival during an era when our telescopes were finally sensitive enough to study it in detail. As 3I/A TLAS continued warming during its approach toward the Sun, one thing became clear. This visitor wasn't following the rules that governed normal comets. It was breathing in space, but the breath carried chemical signatures from a world none of us had ever imagined. Imagine opening a bottle of soda and instead of carbon dioxide bubbles, water vapor poured out. That's essentially what 3I/A TLAS was doing to our understanding of comet chemistry. Everything about its molecular signature was backwards from what astronomers expected to find in a visitor from another star system. When the James Webb Space Telescope turned its infrared eye toward this interstellar wanderer, the results were so unexpected that research teams initially questioned their instruments. The spectrum showed clear, strong emission lines from carbon dioxide, but the water signatures that should have dominated were strangely muted. The numbers told an impossible story, an 8-to-1 ratio of carbon dioxide to water. To put this in perspective, that's like finding a person whose body is mostly carbon instead of water. It violates everything we understand about how icy objects should behave in space. Most comets are basically dirty snowballs, chunks of water ice mixed with dust and trace amounts of other frozen gases. When they warm up near a star, they release primarily water vapor, creating the beautiful tales we associate with these cosmic visitors. Carbon dioxide is usually a minor component, maybe 10% of the total gas production. But 3I/A TLAS was flipping that script entirely. Its chemical signature suggested it had formed in an environment where carbon dioxide was abundant and water was scarce. The question was, where in the universe could such conditions exist? The carbon dioxide dominance wasn't just unusual, it was physically challenging to explain. In most star systems, water should freeze out at greater distances from the central star than carbon dioxide. The zones where planets form should naturally favor water-rich objects over carbon-rich ones. One possibility was that 3I/A TLAS had formed in what astronomers call a carbon dioxide snowline, a region around a young star where temperatures were just right for carbon dioxide to condense while water remained gaseous. But such environments should be rare. Another explanation involved radiation processing during the object's millions of years wandering between stars. Cosmic rays can break apart molecular bonds and rearrange chemical structures. Perhaps 3I/A TLAS had started with normal comet chemistry, but interstellar radiation had slowly converted its water into carbon dioxide. The extended carbon dioxide cloud made the mystery even deeper. Observations from the SPHEREx mission revealed that the gas emissions stretched outward for nearly 350,000 kilometers, roughly the distance from Earth to the Moon. For a nucleus estimated to be only a few kilometers across, to generate such an enormous gas cloud seemed to violate basic physics. It would be like a small campfire somehow heating an entire city. The water detection controversy added another layer to this chemical puzzle. Early observations had detected hydroxyl radicals, molecules that typically indicate water being broken apart by solar radiation. But later, more sensitive observations found water signatures well below detection thresholds. Either the water was there but hidden by some surface process, or our understanding of how hydroxyl forms in comet environments needed serious revision. The chemistry was telling a story, but it was written in a language we barely understood. As 3I/ATLAS continued warming during its approach to the Sun, this alien chemistry would face its ultimate test. Would the molecular ratios change as temperatures increased? Or would the carbon dioxide dominance persist, confirming that we were studying material from a truly alien planetary environment? The universe had delivered a chemistry lesson from another world, but the lesson was written in molecules we'd never encountered before. In the vast emptiness of space, hitting anything by accident is virtually impossible. So when astronomers calculated 3I/ATLAS's trajectory through our solar system and realized how perfectly it was positioned for observation from Earth, some began to wonder whether accident was the right word. The visitor's path was threading a cosmic needle with mathematical precision. Its closest approach to Earth would be 1.88 astronomical units, roughly 270 million kilometers, far enough to be completely safe, but close enough for detailed study with our most powerful telescopes. The geometry got even more intriguing when astronomers plotted the complete trajectory. 3I/ATLAS would pass perihelion on October 29, 2025, at a distance of about 1.4 astronomical units. That placed it squarely between the orbits of Earth and Mars, in the sweet spot where solar heating would drive maximum activity without destroying the object entirely. For an interstellar visitor arriving from the random directions of galactic space, this trajectory seemed almost engineered for optimal scientific observation. Like a cosmic billiard ball that had somehow calculated the perfect bank shot to end up exactly where Earth-based astronomers could study it most effectively. The timing was equally convenient. Unlike Oumuamua, which was discovered when already racing away from the Sun, or 2I/Borisov, which required months of preparation, 3I/Atlas was caught at the perfect moment. Far enough out to plan comprehensive observations, close enough to begin detailed study immediately. Some researchers calculated the probability of such optimal viewing geometry occurring by chance. The numbers were small but not impossible. In the vast lottery of cosmic trajectories, eventually some visitor would arrive with perfect timing and positioning. But others pointed out subtler aspects that raised eyebrows. The orbital inclination was only about 39 degrees. Most randomly oriented interstellar objects should show much higher inclinations, arriving from directions that reflect their chaotic ejection from distant planetary systems. The approach direction also seemed convenient. 3I/ATLAS was coming from the constellation Lynx, a region that would be optimally positioned for observation by both northern and southern hemisphere observatories during its closest approach. Even the visitor's activity patterns seemed designed for maximum observability. It had begun outgassing at distances where most comets remain dormant, ensuring that telescopes could detect its coma and classify it as an active object. The Mars encounter added another layer of convenience. On October 3, 2025, 3I/ATLAS would pass within 29 million kilometers of the red planet, close enough for Mars orbiting spacecraft to potentially capture images during Earth's observational blackout period. It was as if someone had calculated the perfect grand tour of the inner solar system, timing each encounter for maximum scientific value while maintaining safe distances from all planetary bodies. The skeptical explanation was straightforward. Our survey systems are biased toward detecting objects with certain brightness characteristics, approach angles, and activity levels. We naturally find more visitors that are optimally positioned for observation, because those are the only ones our instruments can detect. But the optimized trajectory raised a more unsettling possibility. What if 3I/ATLAS wasn't following a random path through space? What if its journey to our solar system had been planned, calculated, executed with precision that spoke not of cosmic coincidence, but of cosmic intelligence? The mathematics of orbital mechanics don't lie. 3I/ATLAS was indeed threading the needle with remarkable precision. The question was whether we were witnessing an extraordinarily lucky accident or something far more intentional. When astronomers realize they're looking at something unprecedented, the response is swift and coordinated. Within 24 hours of 3I/ATLAS's discovery, observatories worldwide were reorganizing their schedules, redirecting their most powerful instruments toward this cosmic visitor racing through our neighborhood. The cascade began with the Minor Planets Center at Harvard, the global clearinghouse for asteroid and comet discoveries. Their computers calculated preliminary orbital elements and immediately flagged the object as hyperbolic. This wasn't just another space rock. This was an interstellar visitor, only the third ever confirmed. NASA's Planetary Defense Coordination Office issued rapid assessment bulletins. While 3I/ATLAS posed no collision threat, its unusual characteristics demanded immediate attention from the international astronomical community. Priority observing requests went out to every major telescope facility on the planet. The Hubble Space Telescope interrupted its carefully planned schedule. Time allocated years in advance for studying distant galaxies and exoplanets was suddenly reassigned to track this visitor from another star system. The James Webb Space Telescope added 3I/ATLAS to its target list, preparing to turn humanity's most sensitive infrared eye toward whatever was approaching. Ground-based observatories from Hawaii to Chile coordinated their efforts through international networks. The Gemini North Telescope in Hawaii began tracking the object's brightness. Its twin, Gemini South in Chile, prepared to take over as the visitor's position shifted. The Very Large Telescope readied its adaptive optics systems for high-resolution imaging. But this wasn't just about big science facilities. Amateur astronomers worldwide received alerts through established networks. Backyard telescopes that normally focused on Saturn's rings or the Orion Nebula were redirected toward this faint moving dot that carried news from another star system. The coordination resembled a military mobilization. Telescope time worth millions of dollars was reassigned on the basis of preliminary orbital calculations. Research programs planned for years were postponed to accommodate this cosmic visitor that would offer only one chance for study. What made this response different from previous interstellar discoveries was the timing. Unlike Oumuamua, which was found when already leaving, 3I/ATLAS had been caught early enough to plan comprehensive observations. The astronomical community had months to study this visitor as it approached perihelion. The European Space Agency coordinated tracking efforts across their global network. The Chinese Academy of Sciences redirected resources from their major observatories. Even countries without significant astronomical infrastructure contributed computational resources and analysis expertise. Radio telescopes joined the campaign, listening for any electromagnetic emissions that might indicate unusual activity. The Search for Extraterrestrial Intelligence Institutes added 3I/ATLAS to their target lists, monitoring frequencies where artificial signals might appear. The data began flowing back within days. High-resolution images revealed the fuzzy coma that marked this object as active. Spectroscopic observations detected the unusual chemistry that would dominate discussions for months. Perhaps most importantly, the global response revealed something about human nature when confronted with genuine cosmic mystery. Despite different languages, cultures, and political systems, astronomers worldwide dropped their normal research to focus on this single small object racing through space at impossible speeds. The collaboration happened spontaneously, driven not by formal agreements, but by shared curiosity about a visitor that might answer fundamental questions about how planetary systems form around other stars. As data continued streaming in from observatories on 6 continents, one thing became clear. Whatever 3I/ATLAS turned out to be, we would understand it through the combined effort of the entire human species, working together to decode a message written in starlight. When the Hubble Space Telescope turned its unblinking eye toward 3I/ATLAS on July 21, 2025, the image that emerged was both beautiful and deeply troubling. Floating against the star-scattered background was a teardrop-shaped cocoon of dust and gas, glowing softly in reflected sunlight. The nucleus itself remained frustratingly unresolved, appearing as nothing more than a bright point source buried within its own atmospheric shroud. Hubble's exceptional optics could only place an upper limit on the size, no more than 5.6 kilometers across. For perspective, that's smaller than most cities, yet this tiny fragment was generating an atmosphere thousands of miles in diameter. The imaging technique created an accidental work of art. By tracking the comet's motion against background stars, keeping 3I/ATLAS perfectly centered, the telescope created streaks of starlight that made the visitor appear to be flying through a tunnel of light. But the beauty masked a scientific puzzle. The comet's shape was wrong, subtly but significantly different from expectations. Most comets develop prominent anti-solar tails, streams of material blown away from the sun by radiation pressure. In 3I/ATLAS, this feature was puzzlingly faint, almost invisible. The geometry seemed designed to frustrate observers. Either we were viewing the tail from an angle that compressed it into near invisibility, or the dust particles being released were somehow resisting the solar wind's influence. Both explanations challenged conventional understanding. The dust loss rates that Hubble measured provided another puzzle piece. 3I/ATLAS was shedding material at rates comparable to solar system comets at similar distances. This should have been reassuring evidence of normal behavior, except for one crucial detail. This object had been wandering interstellar space for millions of years. Cosmic radiation should have altered its surface chemistry in fundamental ways. Yet here it was, behaving like a comet, making its first passage through the inner solar system. The brightness measurements revealed another anomaly. 3I/ATLAS was reflecting more sunlight than expected for an object of its estimated size. Either the nucleus was larger than Hubble's constraints suggested, or its surface possessed unusually high reflectivity. Hubble's observations hinted at structure within the coma itself. The dust distribution wasn't perfectly smooth. There were subtle variations in brightness and density that suggested active regions on the nucleus surface, specific locations venting material into space in controlled patterns. But without the ability to resolve surface features directly, those patterns remained as cryptic as ancient hieroglyphs. We were studying this visitor through the fog of its own making, like trying to examine a lighthouse bulb while standing in its beam. The photometric data showed remarkable stability over time. Unlike typical tumbling asteroids or active comets, which display brightness variations as different surface regions rotate into sunlight, 3I/ATLAS maintained steady luminosity. Its outgassing seemed almost managed. As August progressed, Hubble continued monitoring the visitor's evolution. The coma was growing, expanding as solar heating intensified, but the nucleus remained unresolved. Each new image confirmed the object's activity while adding to the mystery of its nature. The telescope that had revolutionized our understanding of the universe found itself essentially defeated by a chunk of ice and rock, barely larger than a mountain. We could see that something extraordinary was happening, but the details remained locked behind a veil of reflected starlight. 3I/ATLAS had revealed just enough to confirm its strangeness without explaining its nature. This ancient wanderer continued its journey, now illuminated by our sun's light and scrutinized by humanity's finest instruments, yet remaining as unknowable as when it first appeared as a dot moving against the stars. When humanity's most powerful space telescope focused its infrared sensors on 3I/ATLAS, the results shattered every assumption scientists had built about interstellar chemistry. The James Webb Space Telescope found itself confronting a mystery that challenged everything we thought we knew about how worlds form around other stars. The spectrum that emerged from Webb's observations on August 6th told an impossible story. Instead of the water-dominated signature astronomers expected, The data showed overwhelming evidence for carbon dioxide. Not just a little mixed with water vapor, but a completely backwards chemical ratio that made no sense. The numbers were stark. 8 parts carbon dioxide to 1 part water. Most comets in our solar system show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most unusual, water-poor comets rarely exceed carbon dioxide ratios of 2 to 1. But the chemical surprise was only the beginning. When the SphereX mission mapped the extent of this carbon dioxide emission between August 8th and 12th, they discovered something that defied comet physics. The gas cloud wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 350,000 kilometers. That's nearly the distance from Earth to the Moon. For a nucleus estimated to be only a few kilometers across to generate such an enormous atmosphere seemed to violate basic energy conservation. The spectroscopic fingerprints revealed molecular signatures that spoke of formation conditions unlike anything in our solar system. The carbon dioxide showed characteristics that suggested it had condensed from a gas cloud with different temperature and pressure conditions than those that formed our planets. Webb's infrared sensitivity allowed detection of trace compounds that ground-based telescopes couldn't observe. Alongside the dominant carbon dioxide, there were hints of organic molecules, compounds containing carbon and hydrogen, that might indicate processing by cosmic radiation during the object's interstellar journey. But the water mystery deepened with each observation. Early reports from the Swift Observatory had detected hydroxyl radicals, molecules that typically form when solar radiation breaks apart water vapor. Yet Webb's more sensitive observations found water signatures well below detection thresholds. Either the water was there but trapped beneath the surface, or our understanding of how hydroxyl forms in cometary environments needed fundamental revision. The chemistry was telling a story, but it was written in a molecular language we barely understood. The extended carbon dioxide cloud presented its own physical puzzle. How could such a small nucleus maintain gas production across such an enormous volume? The energy budget demanded either extraordinary activity levels or some mechanism that distributed gas sources across a much larger area. Some researchers proposed that 3I/ATLAS might be fragmenting, releasing carbon dioxide-rich chunks that continued to sublimate as they spread away from the main body. Others suggested that solar-wind interactions might be amplifying the apparent size of the emission region. The isotopic ratios could provide crucial clues about where 3I/ATLAS formed. But detecting isotopes in such a faint, distant object pushed Webb's capabilities to their limits. The preliminary data suggested isotope ratios consistent with formation around a different type of star than our Sun, but confirmation would require months of additional observations. As Webb continued monitoring this interstellar visitor, each spectrum added pieces to a chemical puzzle unlike anything in the scientific literature. We were looking at material from an alien planetary system, chemistry that encoded the temperature, pressure, and radiation conditions of a world we could never visit. The universe had delivered a chemistry textbook from another star system, but the lessons were written in molecules we'd never seen before. To understand why 3I/ATLAS was so puzzling, you need to meet the two cosmic wanderers who preceded it. Each interstellar visitor has arrived with its own personality, its own mysteries, and its own way of challenging everything astronomers thought they knew about the space between stars. Oumuamua was the first, discovered in 2017 by the Pan-STARRS telescope in Hawaii. The name means scout in Hawaiian, and it lived up to that designation by showing us how little we understood about interstellar objects. Oumuamua looked like nothing anyone had seen before, a tumbling cigar-shaped rock perhaps 400 meters long, but only 40 meters wide. What made Oumuamua truly mysterious wasn't its shape, but its behavior. As it moved away from the sun, the object began accelerating in ways that gravitational physics couldn't explain. The acceleration was tiny, but it was real and measurable. Comets accelerate all the time as outgassing creates tiny rocket effects. But Oumuamua showed no visible coma, no tail, No signs of releasing gas or dust. It was accelerating like a comet while looking like an asteroid, creating a contradiction that spawned dozens of research papers. Some scientists proposed exotic explanations. Hydrogen outgassing too faint to detect, radiation pressure on an unusually reflective surface, even speculation about artificial origins. But Oumuamua tumbled away into interstellar space before anyone could solve the mystery definitively. Then came 2I/Borisov in 2019, discovered by amateur astronomer Gennady Borisov using a homemade telescope. If Oumuamua had been the mysterious stranger, Borisov was the familiar friend bearing exotic gifts. Here finally was an interstellar visitor that looked and behaved like a proper comet. Bright coma, prominent tail, steady outgassing. But Borisov carried its own chemical surprise. While it looked normal, its composition told a story of formation in an environment colder than the outer reaches of our solar system. The carbon monoxide to water ratio was unlike anything seen in local comets. Borisov was reassuring in its conventionality, proof that most interstellar visitors would probably be recognizable variations on familiar themes. It followed predictable physics, its trajectory matched gravitational models perfectly, and its chemistry, while unusual, fit within the range of what theories could explain. Now 3I/ATLAS had arrived as the third act in this cosmic drama, and its chemistry was turning the progression upside down. Where Oumuamua showed no detectable outgassing and Borisov showed elevated carbon monoxide, 3I/ATLAS was dominated by carbon dioxide. The pattern seemed designed to sample different aspects of interstellar chemistry. The morphological contrasts were equally striking. Oumuamua's extreme elongation suggested either natural fragmentation or something more geometric. Borisov appeared conventionally spherical with normal coma development. 3I/ATLAS fell somewhere between these extremes, with a compact coma and subtle tail that followed its own rules. The discovery circumstances also revealed how much our detection capabilities had improved. Oumuamua was found when already racing away, discovered almost by accident. Borisov was spotted while still approaching. 3I/ATLAS was caught at the optimal moment, far enough out to plan observations, but close enough to begin detailed study immediately. Each visitor seemed to represent a different sampling of the vast population of debris wandering between stars. Together, these three personalities painted a picture of interstellar space as a realm of extraordinary chemical and physical diversity. The universe seemed to be systematically challenging every assumption we made about what interstellar debris should look like. Just when astronomers thought they understood the category, another visitor arrived to rewrite the rules entirely. Water is the most common frozen compound in the universe. It forms easily around stars, dominates comet chemistry, and creates the spectacular tales we associate with these cosmic visitors. So when 3I/ATLAS arrived and seemed to contain almost no water at all, astronomers faced a puzzle that challenged everything they understood about icy objects. The mystery began with conflicting observations that read like a scientific detective story. Early detections by the Swift Observatory found clear evidence of hydroxyl radicals, molecules that form when solar radiation breaks apart water vapor. The presence of OH suggested substantial water outgassing, exactly what theory predicted. But when more sensitive instruments looked for the water itself, they found almost nothing. The SphereX mission's infrared mapping detected water signatures well below expectations. The James Webb Space Telescope's spectroscopy showed robust carbon dioxide emission, while water remained stubbornly faint. It was like hearing an echo without finding the source. The hydroxyl radicals suggested water was being destroyed by radiation, but the water production rates were orders of magnitude higher than direct detection could confirm. Several explanations emerged to account for this contradiction. The most straightforward was instrumental bias. Different telescopes observe at different wavelengths, and water signatures might be more difficult to detect than carbon dioxide under the specific conditions of 3I/ATLAS's coma. But the discrepancy persisted across multiple campaigns using different instruments. Either every telescope was systematically missing the water, or something fundamental was preventing this interstellar visitor from releasing water vapor in expected quantities. The insulating crust hypothesis offered one intriguing explanation. Laboratory studies show that organic-rich mantles can form on surfaces exposed to cosmic radiation. These crusts act like selective barriers, allowing some compounds to escape while trapping others beneath the surface. If 3I/ATLAS had developed such a layer during its interstellar journey, water ice might be abundant in the interior but prevented from reaching the gas phase by overlying material. Carbon dioxide, being more volatile, could escape through cracks or thin spots in this barrier. This would explain why Webb detected clear evidence for water ice in solid form, while gas phase water remained nearly undetectable. The water was there, locked beneath a surface that had been chemically altered by interstellar processing. The thermal gradient hypothesis proposed a different mechanism. As 3I/ATLAS approached the Sun, heating would penetrate gradually, warming different layers at different rates. If carbon dioxide ice existed closer to the surface than water ice, it would begin sublimating first. Radiation processing offered another pathway to water depletion. Cosmic rays streaming through interstellar space can break apart molecular bonds and create new compounds. Over millions of years, this processing might have converted surface water into other molecules, leaving a depleted layer. The extended carbon dioxide cloud added another layer to this mystery. If water was being suppressed by surface processes, how could carbon dioxide production maintain such an enormous gas cloud? The energy budget seemed to demand water sublimation to drive the observed activity levels. Some researchers proposed that 3I/ATLAS might represent a fundamentally different type of comet, one that formed in an environment where carbon dioxide naturally dominated over water. Such conditions might exist around certain types of stars where temperature and pressure favored carbon-bearing compounds. As 3I/ATLAS continued its approach toward perihelion, the water mystery would face its ultimate test. Solar heating would intensify, potentially breaking through any surface barriers that might be suppressing water release. If the missing water was simply hidden, it would eventually reveal itself as temperatures peaked. The universe had presented astronomers with a cosmic magic trick, evidence that water should be there, but an apparent inability to find it when they looked directly. In space, size should be simple to determine. You measure how much sunlight an object reflects, make assumptions about its surface properties, and calculate the dimensions needed to produce that brightness. But 3I/ATLAS was playing tricks with light that made astronomers question basic physics. The puzzle started with Hubble's imaging. Despite the telescope's extraordinary capabilities, the nucleus remained unresolved, appearing as a bright point source buried within its dusty coma. This allowed astronomers to place only an upper limit, somewhere less than 5.6 kilometers in diameter. That should have been straightforward, but the brightness measurements told a more complicated tale. 3I/ATLAS was reflecting more sunlight than expected for an object of that estimated size, assuming normal surface properties. Either the nucleus was larger than Hubble's imaging suggested, or its surface possessed unusually high reflectivity. Both possibilities raised uncomfortable questions. If the object was significantly larger than 5.6 kilometers, why couldn't our most powerful telescope resolve it? The coma wasn't dense enough to completely obscure a nucleus tens of kilometers across. Yet brightness calculations suggested dimensions that might reach 20 or even 30 kilometers. The reflectivity alternative was equally puzzling. Most comets and asteroids reflect only a small fraction of sunlight that hits them, typically between 3 and 15%. Their surfaces are dark, composed of carbon-rich materials that absorb rather than reflect most wavelengths. But if 3I/ATLAS possessed highly reflective surfaces, approaching 50 or 60% reflectivity, it could appear much brighter than its actual size would suggest. Such high albedo values are rare, found mainly on icy moons with fresh, clean surfaces that haven't been darkened by space weathering. The problem was that high reflectivity and extensive outgassing don't usually go together. Objects with bright, icy surfaces tend to be relatively inactive because their clean appearance indicates they haven't been releasing much dust to darken their exterior. Active comets typically appear dark because dust coating dulls their surfaces. 3I/ATLAS seem to be violating this rule, maintaining both high reflectivity and significant outgassing activity. The photometric stability added another layer to the size mystery. Most small objects in space tumble chaotically, their brightness varying as different faces catch sunlight. The tumbling usually results from collision history or outgassing torques that set objects spinning. But 3I/ATLAS showed remarkably stable brightness over weeks of observation. Either it was rotating very slowly, spinning nearly pole-on relative to Earth, so rotation didn't change its apparent cross-section, or its surface features were unusually uniform. Each possibility carried different implications for the object's structure and origin. Slow rotation might indicate a large object that retained angular momentum, but large objects should be easier to resolve with Hubble. Pole-on orientation would be a remarkable coincidence. Uniform surface properties would be unusual for any object that had survived millions of years in interstellar space. Some researchers proposed that 3I/ATLAS might not be a single consolidated object. Instead, it could be a loose collection of smaller fragments held together by weak gravitational and cohesive forces. Such a rubble pile structure might explain both the brightness anomaly and the extended gas production. If the visitor consisted of multiple pieces, each reflecting sunlight independently, the total brightness could exceed what a single consolidated nucleus would produce. The fragments could also provide distributed outgassing sources, explaining the enormous carbon dioxide cloud. The size riddle reflected a fundamental challenge in studying distant objects. Astronomers were trying to understand the physical properties of something smaller than most cities, located millions of kilometers away, obscured by its own atmospheric emissions. Without knowing how big it was, astronomers couldn't calculate its true activity levels, surface composition, or internal structure. As the visitor continued its approach toward perihelion, resolving the size mystery would become crucial for understanding everything else about this cosmic enigma. Astronomy is a science of patience, but 3I/ATLAS was about to test that patience in the cruelest way possible. Just as this interstellar visitor reached its most active phase, passing closest to the Sun and releasing gases at maximum rates, it would disappear completely from Earth's view for nearly 2 months. Solar conjunction is an astronomical fact of life that occurs whenever Earth, the Sun, and another object align in space. From our perspective, the target appears to move behind the Sun's disk, becoming impossible to observe due to our star's overwhelming brightness and the risk of damaging sensitive instruments. For 3I/ATLAS, this cosmic hide-and-seek would begin in late September 2025, just as the visitor entered the most thermally stressful phase of its journey. Perihelion passage on October 29th would occur, while Earth-based telescopes were completely blind to the object's behavior. The timing felt almost deliberately frustrating. Here was an object that had traveled millions of years to reach our solar system, arriving with chemistry unlike anything we'd seen before, following a trajectory perfectly suited for detailed observation. Yet at the crucial moment, when it should reveal its deepest secrets, it would be hidden behind the very star that was driving its activity. The blackout period would last from late September through early December, encompassing not just perihelion, but the entire period when thermal processing should be most intense. During these weeks, solar heating would penetrate deepest into the nucleus, potentially sublimating buried ice layers that had remained frozen during approach. If 3I/ATLAS contained hidden water ice beneath its carbon dioxide-rich surface, perihelion heating might break through any insulating barriers, and reveal the more conventional chemistry that many astronomers expected. Alternatively, if exotic processes were driving the unusual chemical signatures, peak heating might amplify those effects to levels where their nature would become obvious. The anticipated activity evolution followed predictable patterns based on solar system comets. As 3I/ATLAS approached perihelion, outgassing rates should increase exponentially. The coma would expand dramatically, potentially developing the prominent tail that had remained frustratingly subtle during approach. Peak activity typically occurs not at perihelion itself, but several days or weeks afterward, as thermal waves propagate into the nucleus and sublimation reaches maximum efficiency. For 3I/ATLAS, this meant the most revealing observations might come immediately after the object emerged in December skies. The post-perihelion reappearance would mark the beginning of a frantic observational campaign. By December, 3I/ATLAS would be racing away from the Sun at velocities exceeding 150,000 miles per hour. Each day of delay would mean significantly reduced brightness as the visitor receded into interstellar space. Astronomers faced a narrow window bounded by physics and geometry. Too early and solar conjunction would block observations. Too late and increasing distance would reduce the object's brightness below detection thresholds. The sweet spot for post-perihelion observations would last perhaps 6 to 8 weeks. The Mars encounter on October 3rd offered one potential glimpse during Earth's observational blackout. As 3I/ATLAS passed within 29 million kilometers of the red planet, Mars-orbiting spacecraft might capture images that could bridge the gap in Earth-based observations. Several robotic missions in the outer solar system were positioned for potential observations during different phases of the conjunction period. NASA's Psyche mission would pass within 0.3 astronomical units of 3I/ATLAS on September 4th. The European Space Agency's JUICE spacecraft might attempt long-range observations during November, but these opportunistic observations would provide only fragmentary glimpses of what should be the most revealing period in 3I/ATLAS's entire passage through our solar system. The timing question encapsulated a fundamental challenge in astronomy. We can predict where objects will be and what they should do, but the universe operates on its own schedule, indifferent to our observational convenience. When natural explanations start to feel forced, when evidence seems to point in uncomfortable directions, scientists face a moment that tests their commitment to following data wherever it leads. For 3I/ATLAS, that moment came when researchers began to seriously consider a possibility that had been whispered about since discovery. What if this wasn't natural at all? The question wasn't born from science fiction fantasies. It emerged from careful analysis of observational data that seemed to violate the physics of how natural objects should behave in space. Harvard astrophysicist Avi Loeb, who had gained attention for similar speculation about Oumuamua, began publishing detailed analyses highlighting characteristics difficult to explain through conventional comet science. The size-brightness relationship was one of the first anomalies to raise eyebrows. If 3I/ATLAS were reflecting sunlight like a normal asteroid or comet, its observed brightness suggested dimensions potentially tens of kilometers across. But Hubble's imaging constrained the nucleus to less than 5.6 kilometers diameter. Loeb's calculations suggested that matching the observed brightness with size constraints required surface reflectivity approaching 90%, values seen only in fresh ice or highly engineered materials. Natural space weathering over millions of years should have darkened any surface to much lower reflectivity levels. The extended carbon dioxide cloud presented an even more challenging puzzle. For a nucleus only a few kilometers across to maintain gas emission across a volume stretching 350,000 kilometers required either extraordinary activity levels or some mechanism that distributed gas sources across a much larger area than simple sublimation could explain. The energy budget was staggering. If natural sublimation were driving the observed gas production, 3I/ATLAS would need to be releasing material at rates perhaps 100 times more vigorous than typical solar system comets at comparable distances. Yet the visitor maintained remarkably stable photometric behavior, showing none of the chaotic brightness variations expected from vigorous outgassing. Its activity seemed almost managed, as if some mechanism were controlling the rate and distribution of gas release. The trajectory optimization raised additional questions about intentionality. 3I/ATLAS was following a path through our solar system that provided ideal viewing geometry for Earth-based telescopes, arriving at the perfect time in our technological development to be studied by our most advanced instruments. Radio telescope observations had detected no artificial signals, no structured electromagnetic emissions that might indicate onboard electronics or communication systems. But the absence of obvious technological signatures didn't necessarily rule out artificial origins. Any civilization capable of interstellar travel would likely possess technology so advanced that their artifacts might be indistinguishable from natural phenomena. The controlled thermal behavior added another layer to the technological hypothesis. As 3I/ATLAS moved through different solar environments, its temperature evolution didn't follow simple models of passive heating and cooling. Instead, it showed thermal plateaus and gradual transitions that suggested active temperature management. Some researchers proposed that if 3I/ATLAS were indeed artificial, it might represent a probe or monitoring system designed to study solar systems like ours. The visitor's trajectory would provide comprehensive sampling of our local space environment. The probe hypothesis could explain several puzzling characteristics simultaneously. An artificial object might be designed with high reflectivity surfaces to maximize solar energy collection. It could incorporate systems for controlled outgassing that would create the observed coma without requiring natural sublimation. Critics pointed out that extraordinary claims required extraordinary evidence, and the case for artificial origins remained largely circumstantial. Each anomalous observation had potential natural explanations, even if those explanations strained conventional understanding. But the technological hypothesis served an important function in the scientific process. By seriously considering artificial explanations, researchers were forced to develop more rigorous tests for distinguishing between natural and artificial phenomena in space. If 3I/ATLAS were indeed artificial, what would that actually mean? The engineering requirements for creating something capable of interstellar travel, surviving millions of years in the cosmic void, and operating effectively when it reached our solar system, would represent technology so advanced that it might seem like magic. Consider the basics of interstellar travel. Even at 3I/ATLAS's impressive velocity of 130,000 miles per hour, the journey from the nearest star would take roughly 300,000 years. From more distant stars, travel time could extend into millions of years. Any artificial object would need to maintain structural integrity and possibly functionality across timescales that dwarf all human civilization. The materials science alone would be revolutionary. Components would need to resist degradation from cosmic radiation, micrometeorite impacts, and extreme temperature variations of interstellar space. No material technology we possess could survive such an environment while maintaining precision needed for scientific instruments or communication systems. Yet if someone had solved these engineering challenges, the result might look surprisingly similar to what we were observing. A probe designed for interstellar travel would likely be optimized for minimal mass and maximum surface area, possibly resembling the thin, panel-like geometry that seemed to characterize 3I/ATLAS. The controlled outgassing that puzzled astronomers might represent an intentional atmospheric creation system. A probe studying our solar system might release gases to sample how different materials interact with solar wind and radiation. The specific chemistry, dominated by carbon dioxide rather than water, could be designed to test atmospheric processes under different conditions. The visitor's trajectory supported this interpretation. Instead of following a random hyperbolic path determined by chaotic ejection from some distant planetary system, 3I/ATLAS seemed to be threading through our solar system with surgical precision. Its closest approaches to different planets would provide optimal viewing angles for studying their magnetic fields, atmospheric composition, and orbital dynamics. The timing was equally convenient. The probe was arriving during a narrow window of human technological development, when we possessed telescopes sensitive enough to detect and study it, but not so advanced that we might pose a threat to its mission. Communication represented another engineering challenge that an interstellar probe would need to solve. Traditional radio signals would take years to cross interstellar distances, making real-time control impossible. Any probe would need to operate autonomously, making decisions based on programmed objectives rather than remote commands. This autonomy might explain the seemingly intentional aspects of 3I/ATLAS's behavior. Rather than following simple physical laws, the object might be executing a complex mission profile designed to maximize scientific return while avoiding detection or interference. The probe's creators would face interesting decisions about how obviously artificial to make their emissary. Too obvious, and it might trigger hostile responses from whatever civilizations it encountered. Too subtle, and it might be dismissed as a natural phenomenon. The carbon dioxide dominance might represent a deliberate chemical signature, different enough from natural objects to eventually attract scientific attention, but not so exotic as to immediately scream artificial. It would be a calling card that revealed itself only to civilizations sophisticated enough to conduct detailed spectroscopic analysis. Power sources would present another formidable challenge. Solar panels might work in the inner solar system, but would be useless during millions of years of interstellar travel. Radioisotope thermoelectric generators could provide power for millennia, but would need fuel sources and conversion efficiencies far beyond current technology. Perhaps most intriguingly, the probe hypothesis raised questions about what information it might be designed to gather. Obviously, it could study the physical characteristics of our solar system. But what about civilizations that might exist here? Any probe arriving in 2025 would encounter a planet showing clear signs of technological activity. The implications of discovery would be staggering for both species involved. Humanity would learn that we weren't alone, and that other civilizations had achieved capabilities we could barely imagine. The probe's creators would learn that their surveillance target had developed into a technological civilization capable of detecting their emissary. Whether 3I/ATLAS was natural or artificial, it was teaching us something profound about the universe and our place within it. If 3I/ATLAS were artificial, it might be trying to communicate. This possibility drove radio astronomers around the world to point their most sensitive dishes toward the interstellar visitor, listening through cosmic static for any signal that might indicate intelligence behind the chemistry and physics they were observing. The search for extraterrestrial intelligence has spent decades developing protocols for exactly this scenario. Radio telescopes routinely scan the sky for artificial signals, patterns of electromagnetic radiation too structured to occur naturally. But searching for signals from a specific object racing through our solar system presented unique challenges. The Doppler effect complicated every observation. As 3I/ATLAS moved toward and away from Earth at tremendous velocities, any radio signals it might emit would be shifted to different frequencies in predictable but constantly changing ways. Radio astronomers had to track not just the object's position, but also its velocity, adjusting their receivers in real time. Multiple observatories coordinated their listening campaigns to provide continuous coverage as Earth's rotation carried different telescopes into optimal viewing positions. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and the FAST Telescope in China all contributed to a global monitoring network. The frequency choices reflected decades of SETI theory about how extraterrestrial civilizations might attempt communication. The waterhole between 1.42 and 1.66 gigahertz, bounded by emission lines of hydrogen and hydroxyl radicals, represents a naturally quiet region where artificial signals would stand out clearly. But 3I/ATLAS challenged these assumptions by potentially being mobile rather than stationary. Traditional SETI searches assume that alien civilizations would broadcast from planetary surfaces or orbital installations. An interstellar probe would need to communicate while moving at tremendous velocities through changing electromagnetic environments. The monitoring campaigns detected the usual assortment of cosmic radio sources, pulsars with their lighthouse beams, plasma interactions in planetary magnetospheres, and constant chatter of terrestrial interference. But nothing that clearly originated from 3I/ATLAS itself. However, the absence of obvious artificial signals didn't necessarily rule out technological origins. Any civilization capable of building interstellar probes would likely possess communication technologies far more sophisticated than our current radio-based systems. They might use laser communications, quantum entanglement, or physics we hadn't discovered yet. The probe might also be designed to remain silent during its mission, operating in passive surveillance mode that gathered information without revealing its presence. Only if it detected signs of technological civilization might it activate communication systems designed to establish contact. Some researchers proposed that 3I/ATLAS might be communicating in ways we weren't equipped to detect. The controlled outgassing that created its carbon dioxide coma could represent a form of chemical communication, releasing specific molecular signatures that conveyed information. The visitor's thermal management might also encode information. If the object were artificially regulating its temperature through controlled heating and cooling cycles, those thermal variations might represent a communication protocol. The timing of brightness variations offered another potential communication channel. While 3I/ATLAS showed remarkably stable luminosity compared to tumbling natural objects, subtle brightness changes might encode information in ways that appeared random to observers who didn't know the encoding scheme. Radio astronomers also searched for signals that might not originate from 3I/ATLAS itself, but could be responses to its presence. If the visitor were part of a larger surveillance network, its arrival might trigger communications between different components. The galactic background provided another layer of complexity. If 3I/ATLAS were indeed artificial, it might communicate with its creators using directional transmissions aimed towards specific stars, rather than broadcasting in all directions. Earth might not be positioned to intercept such signals. Whether or not 3I/ATLAS was trying to communicate, the search for its signals was preparing humanity for the possibility that we might not be alone in the universe, and that the universe might occasionally send us visitors capable of conversation across the vast distances between stars. Among the exotic explanations for 3I/ATLAS's behavior, one stood out for its elegant simplicity and testable predictions. What if this interstellar visitor wasn't a probe or monitoring device, but rather a piece of infrastructure, a solar sail that had been drifting through the galaxy for millions of years, pushed by the gentle pressure of starlight? The concept of solar sails has fascinated engineers for decades. Just as wind can push a sailing ship across the ocean, the pressure of photons from stars can accelerate objects in space. The effect is incredibly weak, but in the vacuum of space, even tiny forces can accumulate over time to produce significant velocity changes. For a solar sail to work effectively, it needs to be extraordinarily thin and lightweight, with a high surface area to mass ratio that maximizes photon pressure while minimizing inertia. This requirement would naturally produce objects with extreme geometries, thin panels or sheets that might look very much like the elongated low-mass structure that seemed to characterize 3I/ATLAS. The visitor's brightness anomaly suddenly made sense in this context. Solar sails would be designed with highly reflective surfaces to maximize light pressure, potentially achieving the 90% reflectivity values that conventional comet models couldn't explain. Such surfaces would appear much brighter than natural objects while maintaining the thin profile that made direct size measurement difficult. The controlled outgassing also fit the solar sail interpretation. Rather than representing natural sublimation of comet ice, the gas release might indicate structural degradation of ancient materials. A solar sail that had been wandering the galaxy for millions of years would inevitably suffer damage from cosmic radiation, micrometeorite impacts, and thermal stress. As the degraded sail material heated up in our solar system, it might release gases trapped within its structure, creating the carbon dioxide-dominated coma without requiring conventional ice sublimation. The specific chemistry could reflect exotic materials needed to construct a sail capable of surviving interstellar conditions. The trajectory through our solar system provided additional evidence for the sail hypothesis. While natural objects follow paths determined purely by gravitational forces, solar sails experience additional acceleration from light pressure. This could explain the seemingly optimized geometry of 3I/ATLAS's path, as photon pressure gradually nudged it toward a trajectory that maximized exposure to our sun's radiation. The stable rotation and controlled thermal behavior might represent the sail's designed response to stellar radiation. Unlike tumbling natural debris, a functional sail would orient itself to optimize light collection and maintain structural integrity under varying thermal loads. Even after millions of years of degradation, some of these automatic systems might still operate. But the solar sail theory also raised profound questions about origin and purpose. Who had built this infrastructure, and why had they deployed it in interstellar space? Solar sails work best when they have destinations, specific targets that justify the enormous time and energy investment required for interstellar missions. One possibility was that 3I/ATLAS represented part of a vast network of exploration vehicles launched by some ancient civilization to study distant star systems. The sail might have been programmed to visit multiple stellar targets over its operational lifetime, gathering information about planetary formation, stellar evolution, or the distribution of life throughout the galaxy. Alternatively, the object might be infrastructure for interstellar communication or transportation. Solar sails could serve as relay stations, amplifying signals across interstellar distances, or providing navigation beacons for other spacecraft. The age implications were staggering. If 3I/ATLAS were indeed an artificial solar sail, its creators would have launched it millions or potentially billions of years ago. The civilization responsible might have evolved beyond recognition or gone extinct entirely, leaving behind only their technological artifacts to wander the galaxy. Testing the solar sail hypothesis required careful analysis of trajectory perturbations that might indicate light pressure effects. Natural objects show only small deviations from pure gravitational motion. Solar sails would show different acceleration patterns, with forces proportional to solar irradiation. The post-perihelion observations would be crucial for distinguishing between natural and artificial acceleration mechanisms. If 3I/ATLAS were a degraded solar sail, it might show evidence of structural changes as thermal stress caused further material failure. Whether or not 3I/ATLAS turned out to be a solar sail, the hypothesis demonstrated how technological artifacts might appear to civilizations that encountered them millions of years after their creation. The question of age carried profound implications for understanding what 3I/ATLAS represented and where it had come from. Was this visitor a relatively recent ejection from a nearby star system, or had it been wandering the galaxy since the dawn of time, carrying secrets from an era when the universe was young? The thick disk hypothesis emerged from careful analysis of the object's velocity and trajectory through galactic space. Our Milky Way galaxy consists of distinct stellar populations that formed at different epochs. The thin disk, where our Sun resides, contains relatively young stars, rich in heavy elements. The thick disk contains older stars that formed when the galaxy was perhaps half its current age. The velocity vector of 3I/ATLAS suggested membership in this ancient thick disk population. If correct, this interstellar visitor represented material that had been ejected from a planetary system when the universe was fundamentally different from what we observe today. During the thick disk epoch, star formation rates throughout the galaxy were much higher than current levels. Heavy element production was rapidly enriching the interstellar medium, but overall metallicity remained lower than modern stellar environments. Stars formed from gas clouds with different chemical compositions, potentially creating planetary systems with exotic material distributions. If 3I/ATLAS originated in this ancient era, its unusual carbon dioxide-dominated chemistry might reflect formation conditions that no longer exist in our galaxy. The visitor would be carrying chemical signatures from a time when stellar environments favored different volatile compositions than we see in contemporary planetary systems. The survival implications were staggering. Any object wandering interstellar space for billions of years would experience cosmic radiation exposure that would fundamentally alter its surface chemistry. High-energy particles streaming through space can break apart molecular bonds, create new compounds, and gradually erode material from exposed surfaces. Yet 3I/ATLAS appeared remarkably well preserved, showing activity levels and surface properties that seemed inconsistent with billions of years of space weathering. Either the object possessed extraordinary resistance to cosmic radiation, or it represented a much more recent ejection. The fresh arrival hypothesis proposed that 3I/ATLAS had been ejected from a nearby star system within the last few million years, possibly during planetary system instability or stellar evolution. This scenario could explain the object's apparently pristine condition and its ability to maintain coherent outgassing despite its interstellar journey. Recent ejection would require identifying a plausible parent system within reasonable range of 3I/ATLAS's backtracked trajectory. Several candidate stars existed within 50 light-years of Earth, but none showed obvious signs of recent planetary system disruption. The intermediate age scenario suggested that 3I/ATLAS might have been wandering space for millions rather than billions of years, long enough to develop surface processing that could explain its unusual chemistry, but not so long as to be completely degraded by cosmic radiation. Carbon isotope ratios could potentially resolve the age question, but detecting such subtle spectroscopic signatures in a faint, distant object pushed observational capabilities to their limits. Different stellar environments and evolutionary epochs produce characteristic isotopic fingerprints that could identify not just the general age of 3I/ATLAS's parent system, but potentially the specific type of star around which it formed. The durability question extended beyond simple radiation resistance to encompass structural integrity over cosmic timescales. How could any object, natural or artificial, maintain coherent internal structure while experiencing temperature variations, gravitational perturbations, and physical stresses of interstellar travel measured in millions of years? Ice, rock, and metal all undergo slow but inexorable changes when exposed to extreme conditions of deep space. Yet 3I/ATLAS appeared to maintain the structural coherence needed to support controlled outgassing and stable photometric behavior. The age question also carried implications for the possibility of artificial origins. If 3I/ATLAS were indeed billions of years old, it would represent technology that had remained functional across geological timescales, suggesting engineering capabilities that dwarfed anything humans could imagine. As 3I/ATLAS raced toward its hidden rendezvous with the Sun, one spacecraft found itself in the right place at the right time to potentially solve the mystery that had captivated astronomers worldwide. The Mars Reconnaissance Orbiter, stationed around the red planet for over 15 years, was about to become humanity's eyes during the most crucial phase of the interstellar visitor's journey. October 3rd, 2025, marked a rare alignment that space mission planners couldn't have designed better. As 3I/ATLAS swept through the inner solar system on its way to perihelion, it would pass within 29 million kilometers of Mars, close enough for the planet's orbital assets to capture images during Earth's complete observational blackout. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, known as HiRISE, represented our best hope for maintaining visual contact with 3I/ATLAS during solar conjunction. While the camera was designed to photograph Martian surface features, its exceptional optics and sensitive detectors could potentially capture images of the interstellar visitor. The technical challenges were formidable. HiRISE would need to track a target moving at over 130,000 miles per hour, while maintaining precise pointing accuracy needed for useful imaging. The camera's field of view, optimized for surface mapping, would require perfect timing to capture the visitor during its brief transit. But the potential scientific payoff was enormous. These would be the only images of 3I/ATLAS available during the crucial period when thermal stress from solar heating should drive the object to its maximum activity levels. If the visitor were going to fragment, deploy components, or reveal its true nature through dramatic changes, the Mars encounter window represented our only chance to witness those transformations. The viewing geometry from Mars offered advantages that Earth-based observations couldn't match. While our planet would see 3I/ATLAS projected against the sun's glare, Mars would observe the visitor from an angle that might reveal surface features, structural details, or activity patterns invisible from Earth's perspective. If 3I/ATLAS were indeed artificial, the Mars encounter might capture evidence of technological features that had remained hidden during months of Earth-based observations. Solar panels, communication arrays, or structural elements designed for deep space operation might become visible when viewed from this unique angle. The mission team faced complex scheduling decisions about how to optimize the observation campaign. Every image sequence dedicated to 3I/ATLAS meant missed opportunities for Mars surface science, the primary mission that justified the orbiter's operation. But the rarity of interstellar visitors made this a once-in-a-lifetime opportunity. Other Mars assets joined the campaign with their own capabilities and limitations. The Mars Atmosphere and Volatile Evolution MAVEN orbiter could potentially detect any atmospheric interactions if 3I/ATLAS released gases that reached Mars's thin atmosphere. The European Space Agency's Mars Express might contribute additional imaging from different orbital positions. The technical limitations were significant. Even at closest approach, 3I/ATLAS would appear as little more than a bright dot in HiRISE images, possibly accompanied by a faint coma structure. The resolution wouldn't rival Hubble's clarity, but it would provide crucial data during the period when no other observations were possible. Image processing techniques developed for tracking fast-moving objects against stellar backgrounds would be pushed to their limits. The visitor's rapid motion relative to the background star field would require specialized software to extract useful information from brief exposures. The Mars opportunity represented more than just an observational backup plan. It demonstrated how distributed space assets throughout the solar system could provide multiple perspectives on cosmic events that transcend any single planet's viewpoint. The encounter also highlighted the serendipitous nature of space exploration. The Mars Reconnaissance Orbiter had been launched in 2005 with no expectation that it would ever observe an interstellar visitor. Yet 20 years later, it found itself uniquely positioned to contribute to one of the most important astronomical discoveries of the century. As 3I/ATLAS raced toward Mars on its way to perihelion, scientists prepared for what might be our only glimpse of this cosmic mystery during its moment of maximum revelation. The chemistry that made 3I/ATLAS so puzzling might not be impossible after all. Hidden in the physics of planetary formation around other stars was a natural explanation that could account for the visitor's carbon dioxide dominance, without requiring exotic processes or artificial origins? The answer lay in understanding how different stellar environments create different rules for where various ices can form. In any young star system, different compounds freeze out of gas at different distances from the central star, creating chemical zones as distinct as climate belts on Earth. These snow lines mark boundaries where specific molecules transition from gas to solid ice, and their positions depend on the star's temperature, luminosity, and age. Around our Sun, the water snow line lies at roughly 2.7 astronomical units, just beyond the asteroid belt. Inside this boundary, water exists primarily as vapor. Outside it, water ice can condense and accumulate on solid surfaces. This is why the inner solar system is dominated by rocky planets, while outer regions contain icy moons and gas giants. But carbon dioxide has its own snow line, typically located closer to the star where temperatures are warmer than those needed for water ice formation. In our solar system, the carbon dioxide snowline falls at about 1.5 astronomical units. Objects forming in this intermediate zone could incorporate abundant carbon dioxide ice while remaining relatively water-poor. This scenario could explain 3I/ATLAS's chemistry without invoking exotic formation conditions. If the visitor originated in the carbon dioxide snow zone around its parent star, it would naturally contain the molecular ratios we observe: abundant carbon dioxide with minimal water contamination. But not all stars are identical to our Sun, and different stellar properties create different snowline configurations. Low-mass red dwarf stars, the most common type in our galaxy, have lower luminosities that push their snowlines much closer to the central star. Around such stars, the carbon dioxide snowline might encompass a larger volume of the planetary formation region. Conversely, high-mass stars create more intense radiation that pushes snowlines farther outward. Young variable stars might have fluctuating snowline positions that create complex chemical environments during different phases of planetary system evolution. The carbon dioxide dominance in 3I/ATLAS might therefore represent normal chemistry for objects formed around a specific type of star under particular conditions. What seems exotic from our solar system perspective might be commonplace in other stellar environments. Stellar metallicity, the abundance of elements heavier than hydrogen and helium, also influences snowline chemistry. Stars with different metallicities produce protoplanetary disks with different carbon-to-oxygen ratios, potentially favoring carbon-bearing compounds over water. The temporal evolution of stellar systems adds another layer of complexity. Young stars are often more luminous than their mature counterparts, creating different thermal environments during early phases of planet formation. An object like 3I/ATLAS might have formed when its parent star was in a different evolutionary state. Variable stars, which change brightness over time, could create dynamic snowline environments where freezing boundaries migrate inward and outward over thousands of years. Objects forming in such systems might incorporate unusual chemical mixtures that reflect these changing thermal conditions. The disk chemistry itself could favor carbon dioxide over water under specific conditions. Laboratory studies show that carbon dioxide ice can form more readily than water ice in certain temperature and pressure regimes, particularly when catalytic surfaces facilitate molecular assembly. The chemical evidence from 3I/ATLAS suggested formation temperatures of approximately 80 to 120 Kelvin, cold enough for carbon dioxide to freeze, but warm enough that water would remain gaseous. Such conditions might be typical of intermediate zones around red dwarf stars. This natural formation scenario made testable predictions about what additional chemistry might be found in 3I/ATLAS. Objects formed near carbon dioxide snowlines should also contain specific trace compounds that reflect the local chemical environment. The post-perihelion spectroscopy would provide crucial tests of the snowline hypothesis. If 3I/ATLAS contained hidden reservoirs of water ice beneath its carbon dioxide-rich surface, peak solar heating might reveal them through changing emission ratios. The natural explanation for 3I/ATLAS's chemistry was elegant testable, and grounded in well-understood physics. It required only that planetary formation around other stars produce more chemical diversity than we see locally. Space is not empty, and it is not gentle. Between the stars flows a constant stream of high-energy particles that can fundamentally alter any material exposed to them over cosmic timescales. For 3I/ATLAS, millions of years of interstellar travel meant millions of years of slow but relentless bombardment by cosmic radiation that might have completely rewritten its chemistry at the molecular level. Cosmic rays are atomic nuclei accelerated to nearly the speed of light by supernova, black holes, and other violent cosmic events. When these particles strike solid matter, they can break apart molecular bonds, create new chemical compounds, and gradually alter the composition of surface materials through a process called radiolysis. The effects accumulate slowly but inexorably. Over thousands of years, cosmic radiation can penetrate several meters into solid objects, creating a cascade of chemical reactions that transforms ice into organic compounds, breaks apart complex molecules into simpler components, and creates exotic materials that wouldn't occur naturally in planetary environments. For an object like 3I/ATLAS, which had potentially been exposed to cosmic radiation for millions of years, these effects could be profound. The surface might bear little chemical resemblance to whatever materials originally formed around its parent star. Instead, we might be looking at the products of cosmic chemistry experiments conducted over geological timescales. Laboratory studies of cosmic ray effects on ice show that radiation processing preferentially affects different compounds in different ways. Water ice is particularly vulnerable to high-energy particles, which can break apart H2O molecules and create reactive fragments that recombine into organic compounds. Carbon dioxide is more resistant to radiation damage, remaining stable under conditions that would destroy water entirely. This differential processing could explain 3I/ATLAS's chemical signature without requiring exotic formation conditions. The visitor might have started its interstellar journey with conventional comet chemistry, but cosmic radiation gradually destroyed most of its water while preserving carbon dioxide, creating the unusual molecular ratios that puzzled astronomers. The reddish coloration detected in spectroscopic observations supported the radiation processing hypothesis. Cosmic ray bombardment typically creates complex organic compounds that absorb blue light while reflecting red wavelengths, producing the distinctive color signature that several independent observations had detected. The extended carbon dioxide cloud might also reflect radiation effects. If cosmic rays had created a structurally weakened surface layer, solar heating might cause this processed material to release gases more readily than fresh ice, potentially explaining the enormous gas production from such a small nucleus. But radiation processing raised its own puzzles. The cosmic ray flux in interstellar space is relatively low compared to radiation environments around stars or in planetary magnetospheres. Creating the degree of chemical alteration needed to explain 3I/ATLAS's behavior would require either extremely long exposure times or passage through regions with unusually high radiation levels. Supernova remnants represent one environment where cosmic ray intensities could be orders of magnitude higher than average interstellar values. If 3I/ATLAS had passed through such regions during its galactic wandering, it might have experienced radiation doses sufficient to drive extensive chemical processing in relatively short periods. Stellar encounters could provide another source of enhanced radiation exposure. As the visitor passed through different star systems during its journey, it would experience varying levels of stellar wind particles, solar flares, and magnetospheric radiation that could accelerate surface processing. The depth of radiation penetration added another layer to the processing story. Cosmic rays can penetrate several meters into solid objects, creating chemical gradients where surface materials are heavily processed, while interior regions remain relatively pristine. This could explain why solid-phase water appeared to be present, while gas phase water remained nearly undetectable. The processing hypothesis made specific predictions about what additional compounds might be found in 3I/ATLAS's composition. Radiation-processed ice typically produces formaldehyde, methanol, and other organic molecules that could be detectable through high-resolution spectroscopy. Age estimates based on radiation processing rates suggested that creating the observed chemical signatures would require exposure times of millions to tens of millions of years, consistent with relatively recent ejection from a nearby stellar system, rather than billions of years of galactic wandering. The cosmic ray hypothesis provided a natural explanation for how normal cometary material could evolve into something as chemically unusual as 3I/ATLAS. Rather than requiring exotic formation conditions, the visitor's strange chemistry might simply reflect the slow but inevitable effects of cosmic radiation on any object wandering between stars. Beneath the surface of 3I/ATLAS might lie a hidden ocean of conventional comet chemistry, trapped by an insulating barrier that had formed during millions of years of interstellar travel. This invisible layer could explain why the visitor appeared so water-poor, while showing spectroscopic hints that water ice actually existed in abundance just beneath the surface. Laboratory experiments with ice analogues reveal that cosmic radiation doesn't just alter chemistry randomly. It tends to create specific types of materials on exposed surfaces, including organic compounds that can form effective insulation layers. These crusts act like selective barriers, allowing some volatile compounds to escape while trapping others beneath their protective embrace. The formation process is elegant in its simplicity. As cosmic rays strike the surface of an icy object, they break apart water molecules and create reactive chemical fragments. These fragments recombine into more complex organic compounds, polymers, tars, and carbon-rich materials that are much less volatile than the original ice. Over time, this processed material accumulates into a dark insulating mantle that covers the original nucleus. The crust protects the interior from further radiation damage, while also regulating which gases can escape when the object is heated by a nearby star. Carbon dioxide, being more volatile than water at the same temperature, could escape through cracks, thin spots, or porous regions in this insulating layer. Water, requiring higher temperatures for efficient sublimation, might remain trapped beneath the crust even when solar heating should drive vigorous outgassing. This mechanism could explain the mysterious water detections that had puzzled astronomers since 3I/ATLAS's discovery. The Spherex observations showing evidence for solid water ice, while gas phase water remained nearly undetectable, would make perfect sense if abundant water existed beneath an insulating layer that prevented its release. The selective outgassing would also account for the unusual chemical ratios without requiring exotic formation conditions. 3I/ATLAS might contain normal cometary chemistry, but surface processing had created a filter that allowed us to see only the carbon dioxide while hiding the water beneath. The extended gas cloud presented additional evidence for this hypothesis. If the crust were not perfectly uniform, with varying thickness and porosity across the surface, different regions might release gases at different rates. Some areas might vent carbon dioxide freely, while others remained sealed, creating distributed outgassing sources that could explain the enormous coma size. Thermal modeling of insulating layers showed that such crusts could dramatically alter how heat penetrates into icy nuclei. Instead of uniform warming that drives predictable sublimation patterns, the insulation creates complex temperature gradients that could maintain subsurface ice at temperatures well below the sublimation point even during close solar encounters. The stability of 3I/ATLAS's brightness and activity levels supported the insulation hypothesis. Without protective crusts, most comets show chaotic behavior as different surface regions heat up and release material unpredictably. But an insulating layer would moderate these variations, creating the controlled outgassing patterns that characterize this visitor. The hypothesis made specific predictions about what should happen during perihelion passage. As solar heating intensified, thermal energy should eventually penetrate through the insulating layer or cause it to crack and fail. This could trigger the water release that had remained hidden during the approach phase, dramatically changing the chemical signatures in post-perihelion observations. Laboratory measurements of similar materials suggested that such crusts might have thicknesses ranging from centimeters to meters, depending on the cosmic ray exposure history and the original composition of the nucleus. Even relatively thin layers could effectively suppress water outgassing while allowing carbon dioxide to escape. The color changes detected in some observations might reflect properties of the insulating crust itself. Radiation-processed organic materials typically appear red or brown due to complex carbon compounds that absorb blue light. But the insulation hypothesis also raised questions about how such layers could form and survive the various stresses of interstellar travel. Temperature variations during stellar encounters, mechanical stress from thermal expansion, and impacts from cosmic dust should gradually degrade any surface crusts. Perhaps the crusts were self-healing, capable of reforming when damaged through continued cosmic ray processing. Or maybe they represented equilibrium states where formation and destruction balanced over cosmic timescales. The post-perihelion spectroscopy would provide crucial tests of the insulation layer hypothesis. If thermal breakthrough occurred during peak heating, water emission should increase dramatically as the protective crust failed and buried ice began sublimating freely. When 3I/ATLAS finally emerged from behind the sun's glare in early December 2025, it carried the answers that astronomers had been desperate to find. The interstellar visitor had survived its closest encounter with our star, and its post-perihelion behavior would finally reveal whether we had been studying an alien artifact or simply the most unusual natural comet ever discovered. The reappearance marked the beginning of the most intensive observation campaign in small-body astronomy history. Every major telescope that could track the rapidly receding visitor was pressed into service. Time allocated years in advance was suddenly reassigned as astronomers realized this would be their last chance to solve the mystery. The first post-perihelion spectra told a clear story. The carbon dioxide emissions that had dominated 3I/ATLAS throughout its approach remained strong. But now they were joined by something that had been frustratingly absent: clear, unambiguous water vapor signatures. The chemical evolution was exactly what the insulation layer hypothesis had predicted. Peak solar heating during perihelion passage had finally broken through whatever surface barriers had been suppressing water release. The 8:1 carbon dioxide to water ratio was shifting toward values that, while still unusual, fell within the range of natural comet chemistry. High-resolution imaging revealed additional changes that supported natural explanations. The subtle tail that had been barely visible during approach had developed into a more prominent feature, showing characteristic dust and gas patterns expected from vigorous comet activity. The anti-solar tail direction and morphology matched theoretical predictions for radiation pressure effects. The brightness evolution followed predictable patterns as 3I/ATLAS moved away from the Sun. Instead of maintaining the steady luminosity that had characterized its approach, the visitor now showed declining brightness expected as solar heating decreased and outgassing rates dropped. The photometric behavior was entirely consistent with natural sublimation physics. Most importantly, the visitor showed no signs of controlled maneuvers or artificial acceleration that might indicate technological origins. Its trajectory matched pure gravitational models within observational uncertainty, following the smooth hyperbolic path that Newton's laws demanded for a natural object. The extended carbon dioxide cloud began to contract as 3I/ATLAS receded from the Sun, its enormous size finally explained by the combination of unusual surface chemistry and selective outgassing that had created such a carbon dioxide-rich environment around the nucleus. Radio telescopes continued monitoring for any artificial signals that might emerge during this final phase, but the electromagnetic silence remained complete. If 3I/ATLAS had been trying to communicate, it would have revealed itself by now, when maximum solar energy should have powered any onboard systems. The size mystery resolved itself as improved distance measurements allowed more accurate brightness calculations. The visitor was indeed at the smaller end of initial estimates, probably no more than 2 to 3 kilometers across, consistent with Hubble's imaging constraints. Spectroscopic detection of trace compounds provided the final pieces of the puzzle. Organic molecules associated with cosmic radiation processing appeared in the coma, confirming that the surface had indeed been chemically altered during its interstellar journey. The specific molecular signatures matched laboratory experiments on cosmic ray bombardment of ice mixtures. Isotope ratio measurements, pushed to observational limits, suggested formation around a star with slightly different characteristics than our Sun, but well within the range expected for the thick disk stellar population. There was nothing in the isotopic data that required exotic explanations. As January progressed and 3I/ATLAS continued fading, the scientific community reached a consensus that would have seemed impossible during the height of speculation about alien visitors. This interstellar wanderer was natural, albeit the most chemically unusual natural object anyone had ever studied. The visitor was teaching us that the universe contained far more chemical diversity than our solar system examples had suggested. Planetary formation around other stars could produce icy objects with compositions so different from local comets that they initially appeared impossible, but they remained within the bounds of natural physics. By February 2025, 3I/ATLAS had faded beyond detection limits of all but the largest telescopes. Its brief passage had lasted less than 2 years, but it had fundamentally changed our understanding of what was possible in the cosmic neighborhood. The universe had played fair with us after all. The mystery had natural solutions, even if finding those solutions required expanding our models of planetary formation, cosmic chemistry, and interstellar processing. 3I/ATLAS wasn't alien technology, but in some ways, the truth was more profound than any science fiction scenario. This ancient wanderer had delivered something more valuable than evidence of extraterrestrial intelligence. It had shown us that the universe is far stranger, more chemically diverse, and more wonderful than we had ever imagined possible. The visitor's most important gift was perspective. For decades, our understanding of how planets form and comets behave was based almost entirely on examples from our own solar system. We assumed that the chemistry we see locally, water-dominated comets, rocky inner planets, gas giants in outer regions, represented universal patterns that would be replicated around other stars. 3I/ATLAS shattered that assumption. Here was an object that followed the same physical laws that govern everything else in the universe, yet its chemistry was so exotic that it initially seemed impossible. The visitor proved that planetary formation around other stars can produce materials with compositions we had never contemplated. The carbon dioxide dominance that made 3I/ATLAS so mysterious reflected formation conditions in environments unlike anything in our solar system, around different types of stars, with different luminosities and chemical compositions. The snow lines that determine where various ices can form create completely different chemical zones than those we know locally. This revelation carried profound implications for the search for life beyond Earth. If comet chemistry could vary so dramatically between star systems, then the volatile inventories delivered to rocky planets during their formation might also be far more diverse than previously assumed. Some worlds might receive water-rich bombardment, while others could be shaped by carbon dioxide, methane, or molecular combinations we haven't yet imagined. The cosmic radiation processing that altered 3I/ATLAS during its interstellar journey revealed another layer of chemical complexity. Space isn't empty, and objects wandering between stars don't remain unchanged. The slow but relentless bombardment by high-energy particles creates a cosmic chemistry laboratory that operates over millions of years, transforming materials in ways that don't occur in any terrestrial environment. Understanding these processes helps explain not just interstellar visitors, but also the surfaces of moons and asteroids in our own solar system that have been exposed to space radiation for billions of years. The reddish organic compounds detected on many outer solar system bodies might result from similar radiation chemistry operating over different timescales. The insulating crust hypothesis that explained 3 I/ATLAS's selective outgassing demonstrated how surface processes can dramatically alter the apparent chemistry of icy objects. This has implications for interpreting observations of comets, asteroids, and planetary surfaces throughout the solar system. What we see on the surface might not represent what lies beneath. The visitor also revolutionized our understanding of interstellar object populations. Before 2017, we had no confirmed examples of objects from other star systems. Now, with 3 confirmed visitors showing completely different characteristics, we're beginning to realize that the space between stars contains a vast library of samples from different planetary formation environments. Each interstellar visitor is like a core sample from an alien world, carrying chemical signatures that encode the temperature, pressure, and radiation conditions where it formed. As survey systems like the Rubin Observatory begin detecting dozens of such objects per year, we'll build a statistical database of galactic chemistry that reveals how planetary systems form around different types of stars. The global scientific response to 3 I/ATLAS demonstrated humanity's ability to coordinate rapid, sophisticated investigations of cosmic phenomena. Within days of discovery, observatories worldwide were redirecting their most powerful instruments toward this visitor. The collaboration transcended national boundaries, political differences, and competing research priorities. This coordination provides a template for responding to even more unusual discoveries that might await us. If we ever do encounter genuinely artificial objects from other civilizations, the 3 I/ATLAS investigation showed that our species possesses the technological and organizational capabilities needed to study such phenomena systematically. Perhaps most importantly, 3 I/ATLAS reminded us that the universe still holds surprises. Despite centuries of scientific progress and increasingly sophisticated instruments, nature can still present us with phenomena that challenge our assumptions and force us to expand our theoretical frameworks. As 3 I/ATLAS faded back into the interstellar medium, it left behind a changed understanding of the galaxy we inhabit. We now know that the space between stars is filled with chemical diversity beyond imagination, and that our own solar system represents just one example of the countless ways that gravity, chemistry, and time can collaborate to build worlds. The story of 3 I/ATLAS ends where all great discoveries do, not with final answers, but with better questions and improved capabilities for finding those answers. As this interstellar visitor faded back into the cosmic dark, astronomers worldwide were already preparing for the next mysterious arrival from the space between stars. The Vera Rubin Observatory, nearing completion in Chile, represents humanity's next great leap in detecting interstellar visitors. Its 8.4-meter mirror and 3.2 gigapixel camera will map the entire southern sky every 3 nights with sensitivity that dwarfs current survey capabilities. Theoretical estimates suggest this cosmic census could detect anywhere from 1 to 70 interstellar visitors per year. This transformation from anecdotal discoveries to statistical samples will fundamentally change how we study objects from other star systems. Instead of treating each visitor as a unique mystery, we'll begin identifying patterns, correlations, and population trends that reveal the underlying physics of planetary formation across the galaxy. The European Space Agency's Comet interceptor mission, scheduled for launch in 2029, represents our most ambitious attempt to study an interstellar visitor up close. This innovative spacecraft will position itself at a gravitationally stable point in space, ready to redirect toward whatever cosmic wanderer happens to arrive next. Unlike the frantic attempts to organize flyby missions for 3I/ATLAS, Comet Interceptor acknowledges the fundamental challenge of studying fast-moving visitors. We need to be ready before they arrive. The mission will carry instruments specifically designed for high-speed encounters with pristine interstellar material. The rapid response protocols developed during the 3I/ATLAS campaign provide templates for coordinating future observations. The real-time integration of data from space telescopes, ground-based observatories, and spacecraft throughout the solar system created unprecedented scientific synergies. This collaborative framework ensures we'll maximize the return from each brief encounter. The theoretical foundation for understanding interstellar chemistry has expanded dramatically since Oumuamua's discovery. Each visitor has challenged different aspects of our models, forcing researchers to develop more sophisticated frameworks for planetary formation, cosmic radiation processing, and the chemical diversity possible in alien environments. Future visitors will test these expanded theories while potentially revealing formation processes that don't exist anywhere in our solar system. The galaxy might harbor stellar environments so different from our local conditions that their debris would seem impossible by current standards. The search techniques pioneered for 3I/ATLAS, radio monitoring, coordinated spectroscopy, multi-wavelength observation campaigns, have established new standards for studying potentially anomalous objects. Whether future visitors prove to be exotic natural phenomena or something more extraordinary, we possess the methodological tools needed to investigate them systematically. Public engagement strategies developed during the 3I/ATLAS investigation balance scientific honesty with responsible communication. The experience demonstrated how to acknowledge genuine mysteries while avoiding sensationalized speculation that misleads public understanding of the scientific process. Perhaps most importantly, 3I/ATLAS taught us that maintaining scientific skepticism doesn't require dismissing extraordinary possibilities. The investigation seriously considered artificial origins while applying rigorous evidentiary standards that ultimately led to natural explanations. This balanced approach provides a model for evaluating future discoveries. The cosmic perspective that emerges from studying interstellar visitors is both humbling and inspiring. We live in a galaxy where planetary debris regularly crosses the boundaries between star systems, creating connections across light years of space. Each visitor represents a thread in a vast cosmic web that binds distant worlds together through the slow exchange of matter and information. The educational impact has already begun reshaping how we teach planetary science. Students now learn about chemical diversity through examples from other star systems, not just local objects. The expanded perspective prepares them for discoveries that will define their scientific careers. As we prepare for the next interstellar messenger, the lessons from 3I/ATLAS remind us that the universe keeps sending us teachers disguised as mysteries. Each wandering fragment carries news from regions of space and time we can explore in no other way. The next visitor is already out there somewhere, following its ancient trajectory through the galactic night toward an appointment with our telescopes and our curiosity. When it arrives, we'll be ready with better instruments, expanded theories, and hard-won wisdom about how to distinguish between the merely unusual and the truly extraordinary. The conversation between Earth and the cosmos continues, written in the language of chemistry and physics, delivered by messengers that have traveled farther than human imagination could once reach.